and then click, there you go.
Okay, let me introduce the presenters tonight. John Bickel, Dr. John Bickel received his master's in physics from the University of Vermont and master's and doctorate in nuclear engineering from Rensselaer Polytechnic in 1980. He worked in government and industry in the US, Europe, and Asia. He has many years of experience in the domestic and international nuclear power industry, including analysis, design, and licensing of commercial nuclear reactor control and protection systems and safety systems. He served several years as the chairman of the Paris-based OECD Nuclear Engineering Agency Working Group on Electrical Systems. He has done some teaching and technical training on nuclear engineering in the US and abroad, including countries like Ukraine, Czech Republic, and China. After 45 years, he retired. And as an old nuclear guy, he likes to keep busy and currently devotes his research interest to the physics of stars, which is the topic of his presentation this evening. So, John, please proceed.
Thank you, Mehmet. Well, after that introduction, I will jump in with a quote from Hans Bethe, who received a Nobel Prize related to pretty much this subject. And this is from his Nobel Prize acceptance speech in Sweden in 1967, and it was reprinted in an article in Physics Today. Stars have a life cycle, much like animals. They get born, they grow, they go through a definite internal development, and finally they die. This is a picture of Hans. I actually met him when I was, I think, a young student many years ago at a conference in New York. He's an interesting guy from Munich area, and he was teaching at Cornell at the time in the physics department. My motivations for this work, in the 1970s, I was a grad student in nuclear engineering at RPI, and I spent all my time basically dealing with neutron physics and controlled fission reactions. I really never had much time to talk about fusion physics or what goes on in the inside of stars. And I always thought, well, one of these days I'd look into it when I had a little bit more time, like when I was retired. And in 2020, after about 45 years, I decided enough is enough. I'm retired and, become a pensioner and start having fun and travel to interesting places and look at stars. So when all the isolations and, travel shutdowns started, I finally had the time to really get into studying stellar physics of thermonuclear fusion chains in the inside of stars. And in my spare time, I took an old version of MathCAD 15 that I happened to have on the laptop, and I constructed a simulation program to basically perform Gedanken, or as we used to call them, thinking experiments. And the basic problem I was looking at is existing stars out there right now. When you look at them in the night sky, they are a mix of some of the primordial isotopes from the Big Bang, and additionally recycled isotopes, heavier things like carbon and iron and things like that basically were emitted into the universe from past supernova events. The effort I've been looking at lately was focusing on early star formation. In other words, when only primordial isotopes, these are the ones that were created during the Big Bang, if they were the only ones that were present. And why did I do that? Well, it's a simpler problem to analyze. You got fewer species to have to worry about, keep track of. The other thing I found is that it gives you very interesting, simple highlights of the physics of stars. And as an old guy, I thought, keep it simple, you know. So in the beginning, deep space, we know, consists of various forms of free hydrogen and helium with very tiny trace amounts of lithium left over from the Big Bang. And again, I'm excluding recycled materials. I'm only looking at the primordial or the first elements that were out there. Occasionally, these materials would slowly come together, driven by natural gravitational attraction, and form a cluster. As more of the material is attracted to the gas cluster, the density in the cloud of this gas is going to increase. The effect of atoms bumping into each other continually as the material is pulled together by gravity is going to start a kinetic heating of the interior of this gas cluster. More and more of this gas is coming together. It's being pulled in by gravity. Eventually, the gravitational density causes internal temperatures to start to reach the point where, because everything's bumping into each other and it's getting hot, that the electrons get stripped off of the atoms. And we refer to this as a hot plasma state. In other words, you've got a mixture of free electrons floating around and also positively charged ions. As the density-driven temperatures continue to rise, individual nuclei bumping into each other will begin to fuse, and the effect of this is going to further raise the internal temperatures inside this cloud. Now, one of the first things to recognize is that the positive ions, they're repulsive. You've got to have quite a bit of kinetic energy for them to get together, stick, and fuse. And that's one of the key problems of forming a star and having it turn, start to, glow and heat and emit light. Before I go too far, I want to mention the difference between zero and something in a quantity that is very, very small. This it plays a big effect in astrophysics. I'm going to start with a real simple analogy. If a lottery has an individual chance of 1 in 1 million for winning, it's probably not likely that you buy one ticket, you're going to win. On the other hand, if 300 million people buy the same lottery ticket, it's very likely there will be multiple winners. Stellar thermonuclear fusion reactions typically involve combinations of very, very small reaction rates, but with very, very huge densities of material. Thus, if I have a 10 to the minus 10 number that you see, and I've written it out with all the zeros there, you should never round it off to zero and say, oh, that's really just close to zero. And the reason is, if one is dealing with a density of 10 to the 15th items, it would imply 10 to the minus 10 times 10 to the 15th is 100,000 reactions occurring. I'm going to talk about two types of reaction rates, and I will define them and give examples. Reaction rates basically describe the rate at which one or more atoms react with each other and fuse and form something. It can involve creating a new atom by fusing 2 or more atoms into a different species. The other possibility of a reaction is an internal decay in which one atom splits into something else into 2 different species. Reaction rates that we use in astrophysics can either be experimentally measured or calculated. Many of the reactions that people are via experiments. There are, however, some very critical reactions, which is just physically impossible. You'd have to wait forever to wait and see get one reaction to take place. And in that case, the typical approach is to perform a very detailed, complex calculation and get it peer-reviewed and published. And I've got some exact examples of that. Typically, these reaction rates, they depend on the temperature of the plasma, which is typically expressed in millions of degrees Kelvin. Plasma density, bringing back some of you that remember it from chemistry, we're going to express in units of moles, which is a measure of units per cubic centimeter. And if you remember from chemistry, 1 mole equals 6 point yada, yada, yada times 10 to the 23rd items or atoms or nuclei. I'm going to be expressing binary reactions rates and units of K, where the unit has a dimensions of 1 over moles per cubic centimeter per second. Decay reactions where some item physically decays, it's just going to be in units of per second. An example of a binary reaction. I'm going to consider as just a quick example the fusion of a proton, which is basically a hydrogen atom that's been stripped of electron, with lithium-7 occurring at about 1 billion degrees Kelvin. The reaction goes like this. It yields 2 atoms of helium-4, which are in, again, a highly ionized state. It would basically, we call it an alpha particle. The reaction rate based on data is this value. If I assume a density of 10 to the minus 8 moles per cubic centimeter, which looks like a pretty small number, of lithium-7, and the proton density quite a bit, 120 moles per cubic centimeter, I end up with a reaction rate something like this. This would be the reaction rate in moles, but then when I multiply it by Avogadro's number, I go from a really teeny number to 10 to the 11th reactions per cubic centimeter per second. Now, this is typical of astrophysics and what goes on in stars. An example of a decay, I'm just going to take as an example the decay of tritium. Tritium is a rare form of hydrogen. It basically has 1 proton and 2 neutrons in it. It decays, it's unstable, decays to helium-3 with the emission of a beta particle. This is a beta decay process. Very well measured. It's very well known what that decay rate is. If I assume this density, and I assume I've got this decay rate, basically says the overall rate, lambda times the concentration of tritium, I get 10 to the minus 9th moles per cubic centimeter a second. Again, I multiply by Avogadro's number, it's a huge number. 1 times 10 to the 15th atom decays per cubic centimeter per second. Energy release in stars. The energy release in a star occurs when 1 reaction occurs. And so what I've got is a reaction rate times some kind of an energy release. And I'm going to use a Q here, which is not the same you typically find in your textbooks. I'm going to use a Q where I have removed the energy associated with neutrinos. Some of the reactions fusion reactions involve the ejection of a neutrino, and neutrinos basically carry away some of the energy, but they don't react in anything. Therefore, they can't bounce off of things and contribute to kinetic heating of other atoms and molecules. Thus, the Q that I use in this expression neglects energy carried off by neutrinos because they just don't react very often. So they're not going to contribute to heat in the star. Q then is a recoverable energy release in one reaction, and I'm going to use the units of million electron volts, which is a standard energy measurement in physics. Converting it back to what you're used to seeing, 1 MeV equals 1.6 times 10 to the minus 13 watt seconds. Seems very tiny, but you will not be surprised. You're going to multiply it by Avogadro's number and it gets big. The Q does consider the kinetic energy of the particles and photons. A photon is a particle of light, and the reason is they are given off, it's going to bounce around and contribute to the heat in a star. Some of the reactions are going to release what are called positrons. A positron is basically a positively charged electron. When such is emitted into this hot plasma, we're going to assume it very rapidly recombines with a real electron, a positron, a positive charged electron, and a normal negatively charged electron. When that occurs, there is a release of 1.022 MeV of energy. It's the reverse of what we call pair production. There are publicly available data sources that document all of the numbers you need to try and carry out such an evaluation. That's one of the things I found during all the COVID isolations was I found great data sources for studying fusion rates. First one I'm going to bring up is nukeastrodata.org. This is it's actually a U.S. Department of Energy funded site. It's maintained by Oak Ridge National Laboratory in Tennessee. They have on this website extensive data sets on fusion reactions, different isotopes. Basically, pretty much it's a repository of what the current state of the art is in understanding thermonuclear fusion in stars. One can access this thing. I guess you can sign in as a guest if you want to use it in detail. You got to write a nice little email to Oak Ridge and say, I'm not trying to build a hydrogen bomb or something like that. But I found them very helpful in how to search the thing and use it. One of the databases they have incorporated in here, and which I'll reference, is called NACRE, N-A-C-R-E. This is the European Nuclear Astrophysics Compilation of Reaction Rates. They basically come up with pretty much a reaction rate for just about everything you could imagine. Energy release examples. I showed you a minute ago how one would calculate the rate of reaction of a proton fusing with a lithium-7 to form two helium-4 atoms. The energy release turns out to be about 17 MeV per reaction. I do the calculation of to get the energy rate, I get the concentration of lithium, proton, the reaction rate, and then the Q value. Pull it all together, I end up with about 0.29 watts per cubic centimeter. Tritium decay, I'll do the same thing showing how the how the energy release would be calculated. I need to know the concentration of the tritium, the decay rate, and the heat released per decay, which is actually very, very small. Put it all together in an expression, and the number is extremely puny. You're not going to get a lot of heat from this. Now, understanding stellar energy, to do this, you need basically three things. You require knowledge of what are the reaction rates, and I've shown you where they can come from. You need to have some estimate of the density of the species that are reacting, the protons, the helium, the lithium. I also need to know the energy release for each one of the types of reactions being studied. Since the mid-20th century, data has been coming together to allow a fairly complete picture of how these stellar fusion chains actually work. We now have a better picture of what limits the rate of overall solar fusion chains. And we now have a very good picture of what are the primordial starting species in terms of hydrogen isotopes, helium, and lithium. In other words, these would be the initial conditions if you wanted to study them in detail. This is a diagram showing what are the three main recognized fusion chains. I've highlighted with the red arrows the predominant pathway for making helium. Two protons hit each other. They basically form heavy hydrogen, which is deuterium, H2. It ejects a positive electron and a neutrino. 99.77% of that leads to this reaction, which is deuterium and a proton makes helium-3 and a gamma ray. 84% of that fusing of two helium-3s makes helium-4, and it ejects two protons. So it kind of kicks the proton back into a cycle. I put references here. I don't know if people want to see the original papers, but you can dig them up on the internet. They are on, the American Physical Society archive files. There are There are two other chains in here which are a little bit less likely, and they're shown through here and down over here, and I'll discuss these later. What I'm going to emphasize is this first one, which we call the PP1 chain. Turns out to be the predominant way to make helium-4. The PP2 chain, which I'll talk about when we get into where does the energy come from, this turns out to be the predominant way you get energy out of a star, at least a young star, I should say. The other chain, which is quite a bit rarer, turns out to be one of the ways you're going to be basically making heavier elements. Boron and beryllium are going to come out of this other chain, which is called, for lack of better words, is the PP3 chain. Energy release. This is just a table where I've taken the basic reactions and I put the Q values down one side. Again, these are listed in terms of energy that is recoverable in a small, tiny volume, and thus it neglects neutrino energy, which gets carried off and lost out of the center of a star. But it also includes areas where a beta decay, a positron, right, like as an example right up here, that's going to recombine and with an electron that's in the plasma, and you get a little bump. These would be the energy yields that you can see that come out of these various reactions. One of the things when you look at it is you say, oh, some of these reactions are pretty energetic. The proton and lithium, 17 MeV. The helium-3 reaction gives you 12.8 MeV. The one that starts it all off, however, it's kind of small. At any rate, knowledge of the primordial species. These would be what were the initial constituents spit out by the Big Bang, and we could consider as the initial conditions for forming an early star. The primordial species from the Big Bang have been both calculated with, cosmological type, models, and in some cases they've actually been measured. We know pretty well that simple hydrogen makes up about 75.3% of the original hydrogen or the original elements that were made. This is a graph that was produced by NASA following work based on I'm going to have trouble pronouncing it. The Wilkinson microwave anisotropy program, which they measured up until about 2010. They characterized from this measurement, these are theoretical calculations. The bar down here shows what they think is reality based on actual measurement. They express all of the contents typically as a ratio to the hydrogen nucleus or a proton. So the ratio of helium-4 to a proton is about 24%. Helium-3, you can see, is a whole lot less. That's down in here, 0.9 to 1.3 times 10 to the minus 5. 2H, which is deuterium, this is the ratio of deuterium to the proton, is also, again, 1.65 times 10 to the minus 5. And way down on the bottom, we got lithium-7. Estimates from there are in the range of about 1 to 1.5 times 10 to the minus 10 is the ratio. Again, WMAP on this observation is the Wilkinson microwave anisotropy probe data. And one of the curious things that some of you may have heard is that there's a discrepancy between measured and calculated values of the lithium-7. Calculations apparently show about 5.2 times 10 to the minus 10, whereas the measured value is a bunch lower. Now, given that lithium-7 produces a big energy release when it reacts with a proton, it's probably important to really know what the story is. Reaction data off of nuclear Astro org data. This is an example of one of their screens where you basically harvest data off of. You've got basically a chart of all the nuclides, and you basically select the nuclide that you're looking for in the specific isotope, and it gives you all of the available rates that they've got data on. Oops. This is an example of the type of plots that it produces. When I was doing my kind of study of this area, I basically focused on tables, tabular data of the same results. So one of the first things you learn when you start studying the energy of fusion chains in the PP chain is the proton reaction rate is so doggone slow, so incredibly slow, that it basically ends up controlling the rate that anything else can happen. And I've shown down here a plot taken from the NACRA data, off the Oak Ridge website. You look at the numbers, it's 10 to the minus 20th, rising up to, 10 to the minus 15th in this range. Very, very slow. Other species have reaction rates that are quite a bit higher by factors of, 10 to the 20th. The reaction rate is so small for the PP reaction, which starts everything off. It's never been, it's basically, you can't measure it. It's too slow. So the only way to get this curve is based on, exotic quantum mechanics calculations where they try and study the probability of a barrier penetration. And that's been done, and there is published, there's a lot of published research on what the numbers should be, and that is where this value came from, whereas these up here, they can be measured. So I'm going to do some thinking experiments where I take a MathCAD differential equation solver with the initial conditions and run through some thinking experiments. The first one is, what if in this brand new star, there was only hydrogen present? In other words, there's nothing else but hydrogen that got gasified and then stripped of electrons, and it's bouncing into each other. What I did was I took a typical density of what you might find in our sun. Turns out to be about 160 grams per cubic centimeter. That's pretty dense. That works out to 158 moles per cubic centimeter. I got nothing else in there, and I'm going to assume a plasma temperature of about 15 million degrees Kelvin. Again, this is, it's kind of in the range of our sun. The reaction of the protons reacting with it is very, very slow. It does have an energy yield of 1.69 MeV, neglecting the neutrino, but giving you a credit for the positron. This is the kind of simulation results you get. Now I've got down here time in seconds plotted logarithmically, and I'm showing all of the, the various isotopes I looked at. Most of them, they're down in the dirt. Here is the hydrogen or proton concentration over time. And as it slowly dies off, one of the things we see here is the helium-4 concentration starts to, it bumps up. Now, to put a little perspective in it, the age of the sun, our sun, which by the way is not like this model because it has carbon and iron and other goodies in it, it's somewhere down in here. This would be about the age of the sun. What I'm trying to show you is you got billions of years to consume the hydrogen and convert it to helium-4. What I do, one of the things I did was I looked at the starting amount of hydrogen in the form of protons and the end result where it basically goes down to negligible or almost nothing. And what I've done is I've made 39.6 moles of helium-4. The steady state heat production from just bouncing the protons against each other until they stick is pretty small. That's kind of what I would expect. It's a very, very slow reaction going on because how slow that proton-proton reaction is. I put in here, the age of the sun is somewhere down in here, but don't expect our sun to burn out anytime soon. This is an idealized problem, which are always the easy, fun ones to start out with. One of the things that's interesting is to look at the mass balance. I start with a 1 cubic centimeter at the interior of the stellar core. I had 158 moles of hydrogen, and it got converted to 39.62 moles of helium-4. If I compare the 160 grams to the result 158, you have the question, gee, where did the mass go? The total number of nucleons, that means the individual number of protons and neutrons, it's unchanged from the beginning to the end of the reaction, but it weighs less. What happened? What's the magic? And of course, the explanation of the loss of mass is given by E equals mc squared. Change in mass I could express is about 1.4 grams. And doing the calculations, multiplying it by c squared, I end up with 1.26 10 to the 14th watt seconds, which converted to kilowatt hours, which we're more familiar with from our Excel, utility bill, works out to about 35 million kilowatt hours. So that conversion of a few grams of protons to helium made that much energy being released, but it did it over 10 to the 20th seconds. That's a long, long time to burn it out. Now the other interesting question, if you think about it, the energy release from a reaction of a hydrogen atom with deuterium, in other words, a proton deuterium reaction. I'll just jump back and pull that graph up and show it to you. Notice that the energy yield from this reaction is about 5.5 MeV compared with 1.6. So this is a much more energetic reaction than the proton-proton reaction we were looking at. Myself back in. So now what I'm going to do is I'm going to say, hey, suppose we took that same proton density, which is, roughly in the same range of our sun, 158.73 moles per cubic centimeter. I've got it at a plasma temperature of about 15 million degrees. The reaction of the protons goes like this. Here's the 1.69 energy release. And here is that teeny reaction rate. On the other hand, the reaction of the proton with hydrogen-2 or deuterium, the energy release is huge, but my gosh, look at the reaction rate. It is humongous compared to this. Now, if I did a calculation of a star coming together with the primordial deuterium content, using that ratio that we got from NASA, from the microwave anisotropy probe of 10 to the minus 5, work through the energy production rate in watts, I get 2.2 billion watts per cubic centimeter. That ain't going to work too well. Steady state, you couldn't, that's so much heat, couldn't hold it together. The radiant fluxes would, just make it all fly apart. So there's something wrong here. What is it? Well, a more realistic picture is as a primordial cloud of these gases is forming, and it's being pulled together with gravity, the primordial deuterium is going to get burned up very, very early in star formation as the central density of the star starts to increase. So in effect, what you've got going on is the deuterium that was out there is actually like the match that ignites the thing. It's putting out a lot of heat, but you're going to burn it off. So the real issue then is primordial deuterium burns out rapidly until the rate of consumption of the deuterium matches the rate of it being produced via the very, very slow proton-proton reaction. So that's what we call an equilibrium, just like in chemistry. The rate of new deuterium production would be this, and I've had to put in a 1/2 factor on the reaction rate here because they're both the same species. The rate of deuterium consumption via reacting with protons would be this. When an equilibrium exists, this term equals that term, and I can then solve for what the deuterium concentration is as a function of the proton concentration. So I don't really have this huge primordial deuterium content. I've got something a lot lower because it's already in equilibrium with the hydrogen or the proton content. So I'm going to rerun my simulation, same starting densities, but this time I'm going to assume equilibrium deuterium and the same plasma temperature. Here's my equilibrium deuterium. Again, I see the hydrogen content or the proton content dropping off here at somewhere out in the range of 10 to the 17th seconds. The helium-4 is increasing. The deuterium is a lot less, and it's also going to decrease after I burn it out. No other initial species. These things are things that grow up as a result of the fusion chains. The interesting thing you see now is the steady state heat production went up from what it was before. That's because of the deuterium. So now I'm going to throw in everything. Remember that protons are just plain hydrogen, 75.3%. Helium-4 is this ratio, helium-3 is this, and lithium-7. I'm going to do a quick adjustment because I no longer have all hydrogen in there. I've got a mix of hydrogen and helium-4 from primordial sources. Now gives me 69, or basically 69 moles and 22 moles of helium-4. I'm going to rerun the simulation. What we see here is the helium-3 is pretty constant until the proton content starts to die off. Helium-4 does about the same behavior that I make it. The lithium, which I'm also making in the process, it's pretty stable, but it does die off as the proton content dies off. What I am getting is I'm creating beryllium-7, boron-8. I'm even getting things like tritium, a little bit of tritium in here. Same plasma temperature. Again, the whole dynamics are driven by this very, very slow change in the proton content. I want to talk about the dominant energy production pathway. The PP2 chain turns out to be where you get the bulk of the heat, and we can show that with a similar simulation. For extended periods of time, the deuterium, helium-3, helium-4, lithium-7 concentrations, they are locked in an equilibrium with the proton concentration. The beryllium and boron are steadily increasing. The PP2 chain is the dominant energy production pathway, and I'll show you a graph showing that. I plotted here all of the possible reactions that are going on there. And what you see is the total is basically what I get from the proton lithium-7 reaction. And it basically stays out there as long as I've got, a good source of protons for a while. Same plasma temperature. The one difference is now I've gone from milliwatts per cubic centimeter. I'm now up to 20.5 watts per cubic centimeter. Where the energy came from, looking at it really quickly, I have a reaction rate. The concentration of protons was this. The lithium concentration taken from the primordial ratio. I multiply these two together, I get this concentration. This is the reaction rate at 15 million degrees Kelvin. I end up with this value for the reaction rate, and when I multiply it by the Q value of the reaction, here's how I came up with, it kind of verifies it's about 20.5 watts per cubic centimeter. Effects of temperature. The general trend is that with higher temperatures in this plasma, I'm going to get a higher reaction rate and higher energy release. At 15 million degrees K, I had this. This is typical of what I showed previously. One of the things I can use to study what's going on in the reactions, the reactants and the products, is that the proton content gets less than the helium-4 content at about 39.95 million years. I've got a peak of about 20.48 watts per cubic centimeter. If I raise the temperature a little bit from 15 million to 20 million degrees Kelvin, you get a few differences. At that temperature, the time at which the proton content, one of the reactants are basically less than the products shifts to 834 million years. The peak temperature climbs quite a bit. The other thing is that higher temperature causes faster hydrogen consumption, a higher heat rate, more helium-4, and of course, it's going to make more pressure on the inside of a star while this is going on. Now, many people ask, well, what about the CNO cycle? This is the carbon, nitrogen, oxygen cycle. Is it possible in an early star? This is a diagram showing what that cycle looks like. Carbon-12 reacts with a proton, makes nitrogen-13, which decays to carbon-13, which reacts again with another proton, makes nitrogen-14, which can react with a proton, making oxygen-15, which decays into nitrogen-15, which can react again with a proton, ejecting a helium-4, and I'm back to carbon-12. This is the famous cycle that Beta and Weizsäcker identified, I think it was in the late 30s. But basically, it uses further hydrogen, as you can see it here, 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 and here, to make helium-4, like the PP chain, but it additionally makes nitrogen, carbon, and oxygen isotopes. Now, there's one problem with this. The CNO cycle requires somewhere to start with carbon-12 as a catalyst, and it needs high temperatures. The predominant source, like in our star, of carbon-12 is a demise, or like a supernova of a big star, like a Betelgeuse type thing. You wouldn't find this in an early star. Another aspect of it is that this is actually a fairly small helium-4 producer. It's there, but it's primarily in older stars. Carbon-12 is unlikely to be found in new stars unless certain conditions exist. And the reason is the reaction of helium-4 with boron-8 goes to a carbon-11 and a proton. It does not yield carbon-12. It seems unlikely in smaller new stars because the current processes that we understand for making carbon-12 involve what we call a tri-alpha reaction. This is the reaction of 3 separate helium-4 nuclei fusing together at the same time to make carbon-12, and then it ejects a gamma ray. The reaction rate for this, about all I could say is it's insanely small. 10 to the minus 61 if you're in the 15 million degree temperature range. If I took the helium levels typical of our star, or our sun, and put it in there, I end up with a reaction rate of in the order of 10 to the minus 57. So the answer is that's going to be much, much slower than a really slow proton-proton reaction. The only way this can proceed is if I get significantly higher helium-4 temperatures. In other words, is there some way I can get the reaction rate over here by more heat? And the usual ways to get more heat is more material compressed together. Further on, that it is very unlikely in new stars. Newer calculations are actually out there where people are starting to look and say, is it possible that there are other reactions that we haven't thought of? Is there something going on here because it's so rare we haven't thought of it? And the answer is there have been further studies related to what is the actual reaction rate in the low temperature region for this tri-alpha reaction rate. It's still incredibly small. If I increase it up to 10 to the minus 41, it's still a factor of 10 to the 20th smaller than the proton-proton reaction rate. So the real solution to create carbon-12 is that we need temperatures in excess of 500 million degrees Kelvin. When that occurs, the CNO cycle reactions can then proceed, but at the same time, we still have to have protons. This thing is driven by protons. So what happens next? Starting with just primordial hydrogen, helium, and lithium, stars, I've tried to show the pathway that stars create heavier species of beryllium, boron, carbon, nitrogen, and oxygen, driven primarily by the starting hydrogen protons that were out there. When I've begun to exhaust the hydrogen, what appears next are reactions of these beryllium, carbon, boron with helium-4. And this is a list of all the currently known helium-4 reactions with all of these species. But basically, we've got a cycle here where helium-4 burns with these other items or these other other nuclides, making different nuclides and releasing even further energy. So my summary: the rate of fusion and production of new species and heat is rate limited by the extremely slow proton-proton 1 chain. And this tiny, tiny reaction rate is what's driving why it's so slow. The proton deuterium reactions, although they are more likely and they are more energetic, they burn out quickly in star life. The likely role of proton deuterium reactions is igniting the fusion chain, and when an early star is forming and the density is collapsing and things are starting to heat up, it gives it kind of that oomph, if you want to view it that way. The primordial burning of deuterium and lithium-7 from the Big Bang turn out to be the major sources of heat when you're looking at an early star made up of just primordial elements. The conversion of protons over to helium-4 over the long term results in a net loss of overall mass, which is attributable to E equals mc squared. Transition from a PP chain to the CNO chain requires bigger stars, higher density, and very high, much, much higher temperatures. And that, in fact, is the kind of thing that you see. Now, one of the things that I guess I sort of learned in this exercise is the realization that if you don't have that much material coming together, you could still ignite the star because of the deuterium proton reactions. But if there isn't enough mass, it doesn't progress further on down that chain of your main sequence stars. If you get a lot of mass that's in there, yes, it can. It will propagate from hydrogen burning all the way to helium burning and beyond. And that concludes what I was going to say.
Thank you, John. You can maybe stop sharing. Do you have some extras? Or
Nope.
okay, so maybe you can stop sharing the screen and